Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 11, Lesson 4 on defining the sine and cosine functions. When we began Unit 11, I said this is going to be all about trigonometric functions, the sine, the cosine, and the tangent. And yet, when we began this unit, we spent 3 whole lessons just looking at the geometry of circles, the radian measurement system, and the unit circle. Today, we finally start talking about the sine and the cosine function. Tangent's going to have to wait its turn though, as well as 3 additional trigonometric ratios besides sine, cosine, and tangent. Anyway, let's jump right into it. Defining sine and cosine consistently. The sine and cosine functions form the basis of trigonometry. We would like to define them so that their definition is consistent with what you already are familiar with concerning right triangle trigonometry. So let's remember what we learned last year in geometry about right triangle trig. The sine and cosine in right triangles. The sine of angle A is equal to the side length opposite of A divided by the length of the hypotenuse. And the cosine of angle A is equal to the side length adjacent to angle A divided by the length of the hypotenuse, right? And you beat these things to death in geometry, right? You had these right triangles, you'd look at one of the acute angles and you'd say, oh, the sine is that length divided by the hypotenuse, and the cosine was this length divided by the hypotenuse. Now, however we define the sine and the cosine in this course, we want to make sure that this is still true. Because if it's not, then we have to be like, well, sine and cosine in geometry means this, but in Algebra 2 it means that. And they contradict each other, and we don't want that, okay? So whatever we do, it's going to be based on those 2 things. Exercise number 1. Consider the unit circle shown below with an angle theta drawn in standard position. Letter A. Given the right triangle shown, find an expression for sine theta. All right, well, let's do this together. Okay, so again, we've seen the unit circle. We spent a lot of time in the last lesson on that, and it was ugly, right? It was not pretty. But we've got this angle, right, with its initial ray pointing along the positive x-axis, and then we've rotated it up so its terminal ray is looking like that, and therefore that is angle theta. But we can now draw in this right triangle where x, right, is the side adjacent to theta, and y is the side opposite theta because it passes through the point x comma y. And therefore, I can say that the sine of angle theta is equal to the side opposite divided by the hypotenuse, but the side opposite is the y coordinate, and the hypotenuse is equal to 1. And y divided by 1, well, that's just equal to y. So on the unit circle, the sine of the angle drawn in standard position is just the y coordinate of where the terminal ray passes through the circle. Let's take a look at letter B. Given the right triangle shown, find an expression for cosine theta. Well, why don't you pause the video and see if you can do that. Well, I hope you weren't surprised by this. Right? The cosine of angle theta is equal to the adjacent side divided by the hypotenuse, but the adjacent side is equal to the x-coordinate and the hypotenuse is equal to 1, so cosine theta is equal to the x-coordinate. And this is fantastic because we have now defined the sine of an angle and the cosine of the angle using a unit circle. And now we no longer are constrained to having angles that are acute angles. We can have angles that are acute, obtuse, 90, negative, in radians. It doesn't matter, right? And here we go, defining the sine and cosine on the unit circle. We thus define the sine and cosine functions by using the coordinates of the unit circle. They are the first functions that are geometrically defined. Geometrically defined. I want you to consider that for a moment, right? We almost have always defined functions using algebraic formulas. F of x equals x squared plus 2x minus 3. G of x equals the log base 5 of x minus 10, right? Those are algebraically defined, but we are now defining two of the most important functions in all of mathematics by using the geometry of the unit circle. Here we go. For any angle theta drawn in standard position whose terminal ray passes through the point x comma y on the unit circle, a circle whose radius is 1, the sine of the angle is equal to the y-coordinate, and the cosine of the angle is equal to the x-coordinate. Now, I just cannot emphasize this enough. The above definition, this definition, sine of theta is the y-coordinate on the unit circle, and cosine of theta is the x-coordinate on the unit circle, is unquestionably the most important fact to memorize concerning trigonometry. From now until the time you stop working with trig, whether that's in this course, in pre-calculus, calculus, or anything else you do, this is the most important fact. We can now use this along with our work on the unit circle to determine some exact values of cosine and sine. So let's do that. Let's kind of come down here. Exercise number 2. Using the unit circle diagram, determine each of the following values. Check each with your calculator. Some will be irrational, so check their decimal versions. All right, so again, I just want to kind of get a feeling for this so that you're kind of satisfied with this. You found values of sine and cosine of acute angles a ton last year in geometry. And you use them to solve right triangle problems, all right? In other words, you use them to find missing sides and missing angles in right triangles, but only when you had angles that were acute between 0 and 90. Now, let's take a look at letter A. Sine of 30 degrees. Now, the very definition, right, of the sine function is that it is the y-coordinate on the unit circle where the terminal ray passes through the unit circle. So, here I've got this ray, right, passes through 30 degrees. The sine is the y-coordinate, and that is going to be 1/2. Okay? Now, let's verify that for a second. Like, we generally trust our calculator. Let me just clear this out for a second. All right, so where do I want to go? I want to go to my trig functions, and then I'm going to let it cycle that way because it's exciting. And then hopefully I'm going to get it to, no, I'm not. I'm going to go sine. If you want to be like very, very clear that it's 30 degrees. Now, right now, by the way, my calculator, if you look up here, says RAD. Could we go to the board just for a second so it's a little bit bigger? Right by my how charged is my calculator, it says RAD. That's radians. So right now, if I ask my calculator to find the sine of 30, it is going to assume that I mean 30 radians, which is very, very different than 30 degrees. If I wanted to find the sine of 30 degrees, I have two choices. I can either change my mode into degrees, DEG, all right, or let's say I have it in radians. I can actually hit a button right here. That's not it. I can hit this button. I can grab my degree symbol, and I can hit enter. And I have 0.5. Now, we're working right now in degrees, so I'm going to go back to my degree symbol, all right, to make sure I don't have to put the degree in there each time. But sine of 30 is 0.5, which I'm hoping that we're all comfortable with is the same as 1/2, all right? So it's verified. Let's go back into our full screen. Now, that was basically the only one you would have even considered last year because it's an acute angle. Now let's take a look at B. Sine of 240 degrees. Awesome. Well, I'd like you to use our unit circle and the definition of sine to figure out what the sine of 240 degrees is. Well, here we have 240 degrees, and what we see is that the y-coordinate of 240 degrees is negative square root of 3 over 2. Now that is, to put it mildly, an ugly answer, all right? But we can come over here to our calculator. We can say sine, really? of 240. I'm in degree mode now, so I don't need to actually grab my degree symbol. That's an ugly, ugly decimal, but if I do this, negative square root of 3 divided by 2, I will see that it is exactly the same number. Try to get the pointer off of there so that it's not throwing us off. Now again, your calculator is always going to give you the decimal version, especially if you're using the TI Inspire. Some other calculators will give you those exact values in terms of radicals and things like that. But this is all I want to do to be able to really kind of verify that I have this. Now again, last year, if you think about this, last year, because you were defining sine and cosine simply in terms of the sides of a right triangle, there would have been no way to even think about the sine of 240 degrees. But now I can, right? Because now I just simply need to know that the sine is the y-coordinate on the unit circle and the cosine is the x-coordinate. That being said, why don't you figure out what the cosine of 90 degrees is and what the cosine of 180 degrees is in letters C and D. All right, well, the cosine are the x-coordinates. So for 90 degrees, the cosine is 0. And for 180 degrees, the cosine is negative 1. And again, just real quick, those are really easy, right, on the calculator because they're such sort of nice, I mean, you know, it's easy if my calculator is not doing that. Cosine of 0 is 1. And now I'm tempted to just go up here and grab this, and cosine of 180 is negative 1. And again, you wouldn't have even been able to think about that. That would have been like, how do I do the adjacent side divided by the hypotenuse if the angle is 0? You know, how do I do it when the angle is 180? Impossible, right? Okay. So now what I'd like you to do, these are going to get a little bit uglier, right? Figure it out what the sine of 90, the sine of 135, the cosine of 150, and the cosine of 0 are. Okay, sorry. I believe when I went to the calculator, I actually already did cosine of 0 instead of cosine of 90. My apologies for that. All right, anyway, so the sine is the y-coordinate. And at 90 degrees, the y-coordinate is 1. The sine of 90 degrees, therefore, is 1. For 135 degrees, right, which is 3 pi over 4 radians, the sine, again, being the y-coordinate, is positive root 2 over 2. Maybe we'll take a look at that in just a moment so that we see the decimal version of root 2 over 2. The cosine of 150 degrees is the x-coordinate at 150 degrees, which is negative root 3 over 2. You're going to get very sick of the fractions negative root 3 over 2 and root 2 over 2. And now cosine of 0, which we took a look at on the calculator already, is the x-coordinate at an angle of 0 degrees or 0 radians, and that's equal to 1. Let me really quickly take a look at sine of 135 because root 2 over 2 comes up so often that it's kind of nice just to see its decimal version. All right, it's just kind of good to see it. All right, so what did we have? We had sine, yeah, now you're not going to do it, of 135 degrees, 0.707, etc. And remember, in exact form, we saw using 45, 45 right triangles that should be root 2 over 2. And in fact, it is 0.707, etc. All right. Now, again, one thing that can really get lost in the trees here, or weeds, or whatever you want to lose anything in, is the fact that we are finding sine and cosine using this unit circle of all these special angles, 30, 60, 45, 240, things like that. But that doesn't mean that like 50 degrees doesn't have a sine and cosine. It's just not one of these ones that we have labeled, right? And that's really, again, critical to understand. These angles are labeled because they can be, all right? Because we can use the Pythagorean theorem to find the x and the y coordinates at 30 degrees and 45 degrees and 60 degrees. In pre-calculus, you'll see things called trigonometric identities, and we'll see one of those in this course. Even today we'll see it. But you'll see trigonometric identities that will actually allow you to produce trigonometric values for even other angles, all right? But for now, we leave it at that, all right? And let's keep going. Although the unit circle can be used to find the exact values of the sine and the cosine of special angles, it is more important to simply understand how sine and cosine are defined using the unit circle. right? So exercise number 3. The terminal ray of an angle, alpha, drawn in standard position passes through the point negative 0.6, comma 0.8. Letter A. Show that this point must lie on the unit circle. All right, I'd like you to pause the video right now and think about how you would actually go about showing that this point must lie on the unit circle. Pause the video now and see if you can figure out how that's done. Well, anytime we're trying to show whether a point falls on a particular curve or not, we need to substitute it into the equation of that curve and show that it makes it true. All right? So the equation of the unit circle is x squared plus y squared is equal to 1. That's the equation of the unit circle. So if I want to prove that any given point falls on this equation, I have to show that when I substitute that coordinate point into this equation, I get essentially 1 equals 1. All right, well, let's do it. So we'll have negative 0.6 squared plus 0.8 squared is equal to 1. Maybe I should put a question mark there. Negative 0.6 squared you could do on your calculator if you wanted to. That would be 0.36. 0.8 squared would be 0.64. And 0.36 plus 0.64 is 1. 1 is equal to 1. It must lie in the circle. All right, you can even visualize where it would lie, right? It would be like, you know, we'd have something like this, right? Negative 0.6 would be like if this is negative 1 and this is positive 1, it would be kind of like here. And then here, you know, it might be like this. Right, so there's some angle. Right? I don't even know what that angle is. I don't really care what that angle is. But that point lies on the unit circle. But now, without even knowing what that angle is, we can answer letter B. Let's take a look. What is the value of sine of alpha? All right. Well, what's the value of sine alpha? Pause the video now. You know the definition of sine and cosine. You should be able to just write it down. Well, sine of alpha is 0.8, right? Because, right, the sine of alpha will be the y-coordinate, and therefore, the sine of alpha is equal to 0.8. Furthermore, the cosine of alpha would be negative 0.6, but they didn't ask that. So, we don't know what the angle is. I can say it's somewhere between 90 and 180, but I don't know what the angle is. I could figure it out using like the inverse sine and stuff, but we're not going to go there right now. All right, it is important to be able to determine the sign, positive or negative, not sine S-I-N, but sine S-I-G-N, positive or negative, of each of the two basic trigonometric functions for an angle whose terminal ray lies in a given quadrant. The next exercise illustrates this process. All right, so exercise number 4. Use the definition of the sine and cosine functions to determine if they are positive or negative based on where their terminal ray lies. Then test using your calculator on an angle in each of the quadrants. Okay, so here's my point, right? I've got this unit circle, right? And I've got 0 degrees, I've got 90 degrees, I've got 180 degrees, 270 degrees, and then back to 360 degrees. I've also got the negatives, I've got the radians and all that, but let's just leave it there. So if I'm in the first quadrant, quadrant 1, what must be true about sine and cosine? Well, if I'm in quadrant 1, right, and I had some xy point, right, both x would be positive and y would be positive. And therefore, since y is positive, cosine is positive, and since x is positive, and let me just do that, cosine would be positive. Okay, what I want you to do is then think, and by the way, that's simple enough. Like, let's say we picked an angle. Let's say we took 40 degrees, something that's not one of our special angles. So like 40 degrees would be a good angle in the first quadrant. Right? And if I took this out, let me just clear everything out, right? And I did, please don't go crazy on me, thank you. Oh no, it did, I thought it wasn't going to. Okay, whew. Sine 40 and cosine 40, and they're both positive. They're not nice numbers, but they're both positive, right? Because they're both in the first quadrant. Now, I know that you could do that to figure out the rest, but I don't want you to do that. I want you to do it by geometry. So now if I took like an angle, let's say, in the second quadrant, right? I want you to think about x and y, think about whether they're positive or negative, and fill that out. Pause the video now and consider that for a moment. Well, in the second quadrant, right, the x-coordinate is negative and the y-coordinate is positive. So since y is positive, sine should be positive, right? Since x is negative, cosine should be negative. Now, to do a particular example, pick a number between 90 and 180, maybe, let's say, I don't know, 100 degrees, right? And if I take 100 degrees, terrified now of this, but maybe I'll just do this. Let's do sine of 100. That's going to be a hoot, the entire unit, that thing going crazy. There I've got a positive sine. And, oh, why didn't I just grab cosine? Oh, yay. Most inefficient math teacher in the world. And there's negative. By the way, I just want to point something out. If you look at all the numbers that we keep getting, they are always between -1 and 1, right? I've never gotten a number like the sine of this angle is 1.7 or the cosine of this angle is 2.3. And that should make sense, right? Because the unit circle lives within -1 to 1 on the x-axis and -1 to 1 on the y-axis. You can never have sine and cosine values that are bigger than 1 or less than -1. You can't have ones that are 1 and -1 if they're at the rightmost or leftmost end or bottom or top. Anyway, let's keep going. I just wanted to point that out. Back here. Okay, what I'd like you to do now is actually fill in both 3 and 4 for quadrant 3 and quadrant 4. Think about whether sine, cosine should be positive or negative based on points that you would plot in those quadrants. All right, well, you know, if I had like a third quadrant angle, both the x and the y would be negative. And if I had a fourth quadrant angle, the x would be positive and the y would be negative. Now I know it's kind of annoying. Sine is y, cosine is x. We tend to think about the x-coordinate first and the y-coordinate second, but I've got sine listed first and cosine listed second. That is what it is, right? I mean, sine, right, is the basis of it all. Cosine is based on sine, right? Now again, if you wanted to test these real quick, in the third quadrant, I would just want an angle between 180 and 270. 200 would work great on that. So I don't know, disaster awaits, but let's do it anyway. So no. So let's, boy, I just, you know, just right away. Anyway, let's do sine of 200. Sine's negative. Let's do cosine of 200. And cosine's negative. And again, notice those two numbers are between -1 and 1, right? Then if we went into our third quadrant, between 270 and 360, I like 300. Ooh, these are all turning out nicely in terms of hundreds. So if I went and I did sine of 300, I'm going to have a negative. And if I did cosine of 300, I have a positive. And a nice positive, 0.5. That's because 300 is one of our special angles, right? It's a multiple of 60. All right, so this is an important analysis to immediately know that if you've got an angle whose terminal ray is, let's say, in the second quadrant, then its cosine is going to be negative because its x-coordinate is negative, but its sine value will be positive because its y-coordinate is positive. All right, side note, right, when you were in right triangle trig work in geometry, you would have never had negative sines and cosines because those were the ratios of side lengths. Okay, let's talk about what's called the Pythagorean identity. Since each point on the unit circle must satisfy the equation of the unit circle, please see 2 exercises ago, we can now state what is known as the Pythagorean identity. Remember, an identity is an equation that is always true. Always true. So, let's take a look at what the Pythagorean identity is. For any angle theta on the unit circle, since x squared plus y squared is equal to 1, this leads to the fact that cosine of theta squared plus sine of theta squared is equal to 1. In other words, right, if I take my cosine value and I square it, and I take my sine value and I square it, and I add them together, I will get the number 1. Always, always, always. Now, what can we do with this? Well, let's take a look at exercise number 5. For an angle alpha, it is known that the sine of alpha is equal to 3/5. Determine all possible values of cosine alpha. Draw a sketch to visualize. Okay, and please note, right, 3/5 is between -1 and 1, right? So it's a valid sine value. So how do we use this particular equation or identity to figure out all possible values of cosine alpha? Well, let's take a look, right? What this equation says is it says that cosine of alpha squared plus sine of alpha squared is equal to 1. Now, I want you to be very clear. Alpha is not 3/5. The sine of alpha is 3/5. So cosine of alpha squared plus 3/5 squared is equal to 1. Well, let's just solve this for cosine of alpha. Cosine of alpha squared plus 9/25 is equal to 1. Now, if I subtract 9/25 from the number 1, I will get 16/25. So cosine alpha squared is 16/25. And now I take the square root of both sides, and of course I'm going to get 2 answers. And I'll get cosine of alpha is plus or minus 4/5. All possible values of cosine alpha. Now it says draw a sketch to visualize. Here's what I mean by that, right? If I draw a small sketch, because that's all I have the room for, of the unit circle, right? I know that the sine of alpha is 3/5. What does that mean, right? Well, sine is the y coordinate. So this thing is saying to me, on the unit circle, y is equal to 3/5. Well, we know up here, y is equal to 1, right? 0, 1. So 3/5 would be maybe like this. Let me just write down y equals 3/5. I'm going to draw that horizontal line in. That intersects the unit circle at 2 locations, one here and one here. And that means there's an angle here where clearly the x-coordinate must be 4/5, and there's an angle here where clearly the x-coordinate must be -4/5. Right? So for an angle, alpha, whose sine is 3/5, its cosine could either be positive 4/5 if it's a first quadrant angle, or it could be -4/5 if it's a second quadrant angle. Now, that problem, they didn't tell us what quadrant the angle was in. Let's look at one where they do. Exercise number 6. An angle theta has a terminal ray that falls in the 4th quadrant, and cosine of theta is equal to 1/3. Determine the value of sine theta in simplest radical form. Now again, think about this for a moment, right? Before we do the Pythagorean identity and stuff like that, right? We've got this unit circle. Remember, this is 1 and this is 1. Remember, this is telling us that x is 1/3. So maybe that's a vertical line, right? X equals 1/3. So there's some angle here where x is 1/3. Some angle here that x is 1/3, but this is the one that we're looking for, right? Because we're talking about a 4th quadrant angle. All right, now this one gets a little messy, gets a little ugly, but I'd like you to play around with it a little bit. See if you can figure out what the sine of theta is, and now there's only going to be one answer because there's only one angle, since I've now told you I'm in the 4th quadrant, right? In the 4th quadrant. See if you can figure out what the sine of theta is in simplest radical form. Now, if you don't like the Pythagorean identity because there's cosine and sine flying around, right, you could just use x squared plus y squared is equal to 1, right, where you know x is 1/3 and you're solving for the negative value of y. Or you could go through it with this, right? So it's really up to you whether or not you want to use xy or whether you want to use sine cosine. I'll use sine cosine for right now. So I'm going to have 1/3 squared plus sine of theta squared is equal to 1. 1/3 squared is 1/9 plus sine of theta squared is equal to 1. Subtract 1/9 from both sides. I'll have sine of theta squared is equal to 8/9. This is going to get a little ugly, okay? Take the square root of both sides. That's going to give me sine theta is plus or minus the square root of 8/9. Okay, now I got to do the annoying work that has nothing to do with trig. That's going to be plus or minus the square root of 4 times the square root of 2 all over the square root of 9. This is me just getting ready to put it in simplest form, and that's going to be the sine of theta is plus or minus 2 root 2 over 3. Oh, yuck. I wish we could just leave it as plus or minus the square root of 8/9, but there's no way the multiple choice answer is going to be that. It's going to be written this way. Sorry. Not my choice. I don't find this simpler than this, but it is what it is. Now, we're getting plus minus, right? Because we've got one up here, and we've got one down here, okay? And of course, we want the one down here because we're told we're in the 4th quadrant, and therefore the sign is negative. So because we're in the 4th quadrant, red comes out, sine theta is negative 2 times the square root of 2, all divided by 3. Oftentimes in these problems, the sine and the cosine values are sort of ugly, okay? And that's when we have sort of like Pythagorean triples that aren't integers, all right? 1/3 is not very nice, whereas in the last problem we had 3/5, and that is rather nice. Okay, let's wrap this thing up. Today was an exceptionally important day in this unit, all right? Because we finally actually saw some trigonometric functions, the sine function and the cosine function. And we took what we learned in right triangle trig, which was the sine was defined as opposite over hypotenuse, cosine was defined as adjacent over hypotenuse, and we oriented ourselves in the unit circle, and that allowed us to then consistently say that the sine of the angle was equal to the y-coordinate where the terminal ray of an angle passes through the unit circle, and the cosine is the x-coordinate where the terminal ray passes through the unit circle. And again, I want to emphasize that is the most important thing that you can memorize in terms of trigonometry. Make sure to know it. All right? It's more important than memorizing radians to degrees. It's more important than memorizing all these root 3 over 2, root 2 over 2 stuff. Memorize that the sine is equal to the y-coordinate on the unit circle and the cosine is equal to the x-coordinate. That will pay dividends again and again in this unit and in future courses that involve trigonometry. Anyhow, we'll use everything that we saw today for the rest of this unit, trust me. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.